All right, class, it is Thursday, February the 2nd, and I'm sorry I'm not being able to be with you. Just got off the tennis court, though. It's actually Wednesday here. And what we need to do today is that we need to learn how to do two simple types of problems. And so hopefully you're finished now with your all of your bonding test corrections. If you have any questions about those corrections, you need to ask me. We'll look at those and we'll discuss those briefly on Friday morning. We'll look at those and then we'll kind of move on. If you haven't finished your naming yet, again, that retest is going to be on Monday during AO for that retest. So if you have any questions on that, you can ask me that in class on Friday as well. And so today we want to just talk about two types of problems: calculating the percent composition, and then given the percent composition, how do we determine the empirical and molecular formulas from that? And so first off, the concept of percent. If I was to want to know in this class, what is the percentage of girls in our class? Think about how would you do that? Okay? I know that you're screaming to yourself. You want to say, all right, you're going to count the total number of girls, and then you're going to divide it by the total number of students. And so the percent is always the part over the whole. What part are we looking for over the whole thing that it's a part of? And so when we're doing percent composition of a compound, we're going to be measuring the part of that that's due to that element over the whole thing. And we're going to do it in terms of mass. I'm going to move the camera just a little bit, give you all a little better angle of the board. Okay? And so there are going to just be two simple steps to calculate your percent composition. So if we want to do something simple, even like, what is the percent of hydrogen and oxygen in water? And it's always percent by mass. Okay, so what's the percent by mass? So what's the part? What's the part that's hydrogen? What's the part that's oxygen? And so to do the first thing we have to do is you have to calculate the molar mass. And this is a review from the past. We get the molar mass of water. And hopefully you remember how to do this. The fact that you're going to you look on the periodic table and you look at the red number, the atomic mass of hydrogen, and you see that it's 1.01. We have two of them. So it's going to be 2 moles times 1.01 grams for every mole. And that's going to equal 2.02 grams of hydrogen. And then the oxygen is going to be 1 mole times 1 mole times the atomic mass of oxygen, which is 16.0 grams per mole. So that's going to be 16.0, really 0, if we want to carry another sig fig, grams of oxygen. So the molar mass is 18.02 grams per mole. That's the molar mass of water. So what the percent composition is saying, okay, well, of this 18.02, what's the percent that's hydrogen? What's the percent that's oxygen? Well, again, it's the part over the whole. So the percentage that's hydrogen is going to equal 2 grams, the total mass, divide the total mass of each element by the molar mass, and then multiply by 100. So the total mass is the 2.02 grams of hydrogen divided by 18.02 grams of water times 100. And that's going to come out to, I believe it's 11.11% hydrogen. And then the percent oxygen then is going to equal 16.00 grams divided by 18.02 grams times 100. And obviously it has to add up to 100%, so this would be the 88.9% of oxygen. So it's a very straightforward. I'm going to go get a calculator and double check that. I really only have to check one of them because 2.02 divided by 18.02 equals 11. Oh, I was off. It's 11.21%. It's 11.2. And so this is going to be 88.8%. Okay? So it's just the part over the whole. So we calculate the molar mass like we've done in the past, and then we just take the part over the whole. So if we want to look at a different one, a different example. So we want, what's the percent of each element in glucose C6H12O6? Okay? Well, first step, find the molar mass. Now we're going to do this one a little bit more shortcut. The molar mass of C6H12O6 is going to be 6 times 12.01 plus 12 times 1.01 plus 6 times 16.0. So that's going to equal 72.06 plus 12.12 plus 96.0, which is all going to add up to 180.18 grams per mole. So that's the molar mass, that's the total weight of the glucose. So if we want the percentage of carbon, it's going to be the part over the whole. The part that's carbon divided by the whole thing, the molar mass. So the percent carbon is going to equal 72.06, because of the 180, 72 grams of it was carbon. So it's the total weight divided by 180.18 grams C6H12O6 times 100. Okay, so we got to work that out. So it's 72.06 divided by 180.18. That comes out to 39.99 or 40.0%. Well, we have 4 sig figs, so we can even say 39.99% carbon. Going to do the same thing for the hydrogen. That's going to equal 12.12 grams of hydrogen divided by the 180.18 grams of the C6H12O6 times 100. So we go 12.12 divided by 180.18. That comes out to 6.727. So again, I have 4 sig figs. So I'm going to say 0.06, well, pardon me, I got to multiply by 100. 6.727% hydrogen. Now, for the oxygen, we do the same thing, or you could just subtract it from 100 because we know the rest has to be oxygen, but it's easier, I think, just to say 96 and we can go one more sig fig since we have 4 on everything. 96.00 grams of oxygen divided by the 180.18 grams C6H12O6 times 100. 96 divided by 180.18. That comes out to 53.28% oxygen. And so if we add all that up, it should come out right to 100%. 53.28 plus 6.727 plus 39.99 equals 99.997. It's just because we carried, if we rounded this to a 3, then we're going to get right to 100. Okay? So everything adds up to 100%. So it's just the part over the whole. Very straightforward. Very easy problem. Everybody, all of y'all should be able to do this quite easily. Now, just one variation of this, which is the same type of thing, but it's doing simple math. Is how many grams of carbon are in a 50-gram sample of glucose, C6H12O6. Make it easy since we already did this. Okay? So we want how many grams of carbon? Well, we just figured out that of the 180.18, 72.06, okay, is always going to be carbon. And so that means it's always going to be in that ratio. So we can kind of just set this up and do our percent composition. We can say that 72.06 grams of carbon in every 180.18 grams of glucose. And we just multiply that. Now really we can set up a proportion, which is say it's going to equal, well, how many grams of carbon then are going to be in 50 grams of glucose, C6H12O6. Now we know to solve for X here, you're going to cross multiply. So you're going to end up getting 72.06 grams of carbon times 180.18 grams of C6H12O6 times 50 grams C6H12O6, and that's over an understood 1. So grams of this cancel. So you're just really saying, okay, rather than dividing this out and getting the 53 point whatever percent we just said it was, okay, the 53.28%, okay, because you just have to divide by 100 again, so we just have this ratio. So 72, so you just put the part over the whole times whatever the mass of the sample is. And that's always going to tell you the part. So if we want to figure out, well, how many grams of hydrogen are there? Well, we would take the mass of the hydrogen, which was 12.12 grams divided by 180 times our 50 grams. The part that we're looking for, percent, because that much, that percent of always means times, of 50 grams equals the grams of carbon. So we can do those types of problems very simply. So if you just want to get the part, the grams in a sample, you just take your percent composition and multiply it by the sample. You can set it up as a proportion if that makes more sense, but the reality is I'm just bypassing this, setting it up, and I'm just going to the solving. This equals X grams of carbon. That equals that. So once we just multiply through, so I always just go straight to this step. Put the part over the whole times the mass of the sample, and that's going to tell you how much. So that's how you do on percent composition. That's all you need to do there. And so it's really quite simple. You do not need to make it challenging. Now, let's go the other way. We want to calculate the empirical formula from percent composition. Okay? The empirical formula. So this, you're given the formula, and we have to find the percent composition. Now we want to go the other direction. So, if a compound was analyzed and found to be, 80% carbon and 20% hydrogen. What is the empirical formula? Okay, so there's your question. So what's the empirical formula? A compound is said to be 80% carbon and 20% hydrogen. Okay, 80% carbon, 20% hydrogen. What's the empirical formula? Now, the law of definite composition says that elements have a definite composition by weight, or compounds have a definite composition by weight. They're always going to be the same. Water is always H2O. Sugar is always C6H12O6. Okay? So it doesn't matter how much of the substance you have, it always has the same composition by mass. So if you have 50 grams, it's going to be the same percent. So it doesn't matter when we just did that percent composition, it doesn't matter what whether it's 50 grams, 100 grams, 1,000 grams, 6.854,321 grams, it's always going to be the same ratio. Water is always H2O. If you have a cup of water, if you have a gallon of water, if you have an ocean of water, it's always H2O. 2 hydrogens to 1 oxygen, 2 grams of hydrogen to 16 grams of oxygen, always. So, no matter how much we pick of this, it's always going to be 80-20. So let's pick a number that makes the math easy. Well, if I choose 100, assume I have 100 grams, well, what is 80% of 100? Well, hopefully you can do that math in your head. 80% of 100 is 80. So if I choose 100 grams, I can just change my percent to grams. So I can say then that I have 80 grams of carbon and I have 20 grams of hydrogen. But when I say the formula, water is H2O, that's not 2 grams of hydrogen and 1 gram of oxygen. That's 2 moles to 1 mole. So we always have to change the moles. So the way that we do that is with the molar mass. We've done that in the past. So we're going to say, since grams on the top, we want grams on the bottom. So we're going to say 1 mole over, look at the red number, 12.01 grams. That's from the periodic table. So I find my atomic mass. So I go 80 divided by 12. 80 divided by 12.01. And that comes out to 6.66 moles. So I have 6.66 moles. I do the same thing for the hydrogen. 1.01 grams. So it's 20 divided by 1.01 is equal to 19.8 moles of hydrogen. So now I have a mole ratio, but it is not a small whole number ratio. So I got to figure out what's my small whole number. Well, if it's in a ratio, this number has to be a multiple of that number. So I divide each by the smallest whole number, 6.66. Well, obviously this is going to be 1. So I go 19.8 divided by 6.66, and that comes out to 2.97, which as terms of, it's close enough in government work to get a 3. Okay, the only reason it's not exactly 3 is the rounding with the molar masses and such. Okay, so that means then that my empirical formula of this compound is equal to CH3. Okay, so that's all I can find. I can find the empirical formula. I just changed the percent to grams, divide by the molar mass to find how many moles of each thing, and then I divide each mole value by the smallest mole value to get a small whole number ratio. Okay? Now, I happen to know that this is not the way the molecule exists. So this is a covalent molecular. It's 2 nonmetals, so it's covalent, so it makes a molecule. So I don't have to have the simplest ratio. So now I need to find, well, what's the molecular formula going to be? How do I get to the molecular formula? Well, the molecular over here, come here, come on. To get the molecular formula, you just take our empirical formula, and I have to calculate the empirical formula mass of it. Okay, that just means that's the mass of the empirical formula, just like we do the normal molar mass, add up the weights. Okay, so I'm going to do that, so I'm going to find my empirical formula mass, my EFM, and it's going to be easy. It's going to be 12.01 plus 3 times 1.01. It's going to come out to equal 15.04 grams per mole. So now I have to be given, though, let's just say the molecular mass is determined to be 60.16 grams per mole. What is the molecular formula? Well, now I'm going to take my given, divide, convert the grams to mole, pardon me, over here. Divide the given molecular mass. That's what we have. That's the 60. By the EFM. So I'm going to say 60.16 divided by 15.04. That equals 4. So I get a small whole number. So that means then that my molecular formula is 4 times the empirical formula. So my empirical formula is going to be CH3 times 4. Now we're not going to leave it in that form. We're just going to multiply through, so it's going to be C4H12 is equal to the molecular formula. This is the way the molecule actually exists in nature. C4H12. Okay? So it just kind of gives us an idea of how the atom is arranged. So it's just going to be follow the individual steps. So let's do another one. Let's do a practice. Let's just do 2 more practice, and then we'll be done, and then I'm going to let you practice. Okay? So the only thing that's going to change are my percentages. So if I look, I'm just going to try and find one in the textbook. And it says, let's come back here I'm looking on page 243 in your book, which you can find on your Chromebook. And I'm looking at a practice problem on the section 4. It says a compound contains 36.48% sodium, 25.41% sulfur, and 38.11% oxygen. Okay? Actually, yeah, so we'll just do this one. All we can do on this one is get the empirical formula. So it's going to be 36.48. I'm going to change percent directly to grams. Sodium. It's going to be 25.41 grams of sulfur. And it's going to be 38.11 grams of oxygen. And the question says, what is the empirical formula? Okay, so it's 36.48% sodium, 25.41% sulfur, and it's going to be 38.11% oxygen. That's what's given. Okay, so what is the empirical formula? So, change percent to grams. That's step 1. Step 2, convert this to moles. So we're going to use the molar mass. 1 mole over 23.0 grams. 1 mole over 32.0708. It is 0.07 grams. And then 1 mole over 16.00 grams. And then we just figure out what each one of those are. So we get 36.48 divided by 23, 1.586 moles of Na. 25.41 divided by 32.07, 0.792 moles of sulfur, and then 38.11 divided by 16 is equal to 2.38. 2 moles of oxygen. So now I have this mole ratio. But it doesn't look like anything. It's got to be a whole number ratio. So to get the whole number ratio, we divide by the smallest one. In this case, it's going to be 0.792. 0.792 and 0.792. Obviously, this one's going to be 1. This one's going to be divided by 0.792, exactly 3. And this one, 1.586 divided by 0.792 equals exactly 2. So that's my small whole number ratio. This is a 1 to 2 to 3 ratio. So it's going to be Na2SO3 is equal to my empirical formula. Okay? Now, if we want to flash back to last chapter, we can name this. And since it's an ionic compound, we're just going to name the positive ion first and negative ion last. Sodium is an alkali metal, so it doesn't need a Roman numeral. So it's simply going to be sodium sulfite. Okay, sodium sulfite. So that's the empirical formula. Now the molecular formula is not given. The molecular mass is not given. So I cannot find the molecular formula of this compound because I don't have the given molecular mass. So all I can do is find the empirical formula. Plus this is an ionic compound, so that's all we get with an ionic compound anyway. We just get the empirical formula. Okay? So, if we just want to look at one more, that was just the empirical formula. Let's look at one more calculating the molecular formula. And we can look on the same page on your Chromebook on that. And this time, it's just going to give us, if we look at number 4 on this, number 4 says you got 4.04 grams of nitrogen and 11.46 grams of oxygen. 4.04 grams of nitrogen plus 11.46 grams of oxygen. And it tells me that the molecular mass is equal to 108. And it just says U, which is atomic mass units, but we'll generally have it in grams per mole. It won't matter. Now notice on this one that it's not given percent, it's given grams. Well, that just saved you step 1. Now we don't have to assume anything. Now we're already in grams, so we just go to step 2. So we have 4.04 grams of nitrogen, and we have 11.46 grams of oxygen. Convert to moles. 1 mole over 14.01 grams. 1 mole over 16.00 grams. Again, both of these numbers are coming. That's the red number off the periodic table. Okay? So then we just figure out what that is. So we say 4.04 divided by 14.01 equals 0.288 moles of nitrogen. And then we get 11.46 divided by 16 equals 0.716 moles of oxygen. So now we divide by the smallest one. 0.288. Obviously this one's 1 divided by 0.288. And this one comes out to 2.5, 2.486. So 2.49, which is really close to 2.5. You cannot round that to 2 or 3. When you get a fraction like this, hopefully you recognize that 0.5 is the same as 1/2. So then we have to multiply this whole thing by 2 so to get a whole number. So we're going to go times 2 times 2. So the ratio is really 2 to 5 is my whole number ratio. So if the rule is that this decimal has to be within like 0.05 of a whole number to be able to just round it. If it's not, usually it's going to come out to 2.33, which means it'd be a third, so we'd multiply by 3. This one is 0.5, which means it's a half, so we multiply by 2. If it came out to 2.25, that would be a fourth, so we'd multiply by 4. Whatever the fraction is on the decimal part, it's going to be a common fraction. And again, it came out to 49, but I know that that's the common fraction is going to be 0.5. So my empirical formula is N2O5. That's my empirical formula. Now, to find the molecular formula, I have to find the empirical formula mass. So that's going to be the EFM is going to equal 2 times 14.01 plus 5 times 16.0, okay, is going to equal 28 plus 90 is going to equal, 80 is going to equal 108 grams per mole. So when I take my given molecular mass up here, 108 divided by 108, that equals 1, which tells me then that my empirical formula and molecular formula are the same. So the molecular formula also equals N2O5. It's the same thing. Just like water. Water is an empirical formula and a molecular formula. It's the way the molecule actually exists. So all you have to do is follow these steps. You just plug it in, convert the percent to grams if need be, convert to moles, divide by the smallest. If it doesn't come out to be a whole number on the first time, multiply it by whatever the decimal part, the common fraction, get a small whole number ratio. That gives you your empirical formula. Then take the given molecular mass, divided by that empirical formula mass, get a small whole number, multiply the empirical formula by that number, and you get the molecular formula. So we have two types of problems: percent composition and empirical formula and molecular formula. So those should be pretty straightforward. So what you can do now is you can practice. So if you go to your book in your Chromebook to page 249, 248 and 249, you can do questions number. Now, let me erase this and I'll put it up here for you. Okay, so we want to move this back to the middle so we can get a clean shot. So we want to go to page 248 and 249. I want you to do numbers 31, 32, 36, 38, and 39. Okay, those would be good practice for you on being able to do these. These are going to be due on Friday, so you can watch the video. If you didn't get enough time, you watch it at home and do these as well. Okay? All right, hope you're having a great day, and I will see you on Friday.